Section 2.2.1 Free Undamped Oscillation. The simplest form of oscillation occurs when a system is undamped and free to oscillate backwards and forwards. The form of oscillation is often referred to as simple harmonic motion. The response x of t will be a sinusoid, and so in this case the solution x as a function of time has the form of a times by cosine of omega naught t plus phi, where a is the amplitude of oscillation, the largest displacement from the equilibrium position. Omega naught is the angular frequency of the oscillation, measured in radians per second, and that's the natural frequency denoted by the naught suffix. And phi is the phase angle which compensates for the correct position when t equals 0. Taking the natural frequency, omega naught, the period of oscillation has the unit seconds is given by 2 pi divided by the natural frequency. The frequency of oscillation, which is measured in hertz and is denoted by f naught, is given by 1 divided by the period, so we end up with omega naught divided by 2 pi. A simple example of such a system is this mass spring system, with mass of m and spring with stiffness k. When the mass is at x equals 0, the spring is in its equilibrium position, but when it's deflected by a distance x, the mass will oscillate backwards and forwards. So yeah, free oscillation. Mass and a spring, you deflect the mass, you let it run, and it goes backwards and forwards forever. Okay, following that equation of a sinusoid. So let's do some maths. Let's apply Newton's second law. Okay, well, obviously Newton's second law, sum of all the forces equals mass times acceleration. So there's my mx double dot, mass times acceleration, and the only force that's being applied to that system is the spring force. Now the force on the spring always opposes motion, so we've got a minus sign, and we've got a stiffness to that spring, which is denoted by k, and obviously the force in the spring is k times the deflection that you've inflicted upon it, so x. So we've got ma equals minus kx. There's no other forces on the system, so it's very simple. We put kx on the other side, so it becomes plus kx, okay, and then we divide everything by m. 0 divided by m is 0, so that disappears, and then obviously we've got x double dot plus kx, plus k upon m times by x equals 0. And that solution applies providing omega is root k upon m, okay? The natural frequency has to be root k upon m, and if that's the case, then this equation is a solution to that equation. We can check that, okay? And we can check that by taking the derivative of x of t, okay, or double the second derivative, and then plugging it back into the equation, and we can find out that omega does in fact equal root k upon m. So there we are, we've taken the second derivative of that equation, and all that happens when you take the first derivative of this equation, obviously cosine turns into minus sine, and an omega naught has to come out because we've got to apply the chain rule, okay? So we get an omega naught and a minus sign coming out. And then obviously take the derivative of that, okay, the minus sign turns into minus cosine, okay, and another omega naught comes out. So we get minus omega naught squared times by essentially the same thing. Okay, so that's what happens. So we get minus omega naught squared coming out, and then notice that a cosine omega naught t plus phi is in fact x, so we can just write minus omega naught squared x. And if you plug that in for x double dot, you get this equation. And obviously the x's can cancel out, and you end up with omega naught being omega naught squared being k upon m, so omega naught must be the square root of k upon m. Okay, so you can show that that equation is the solution to that problem.